Imagine this. A traveller like you drifts into the quiet hours of night guided here not by accident, but by the strange gravity of a question the universe wants you to hear. Above us, an ancient object glides past the edge of Mars, the fastest interstellar visitor ever found moving at over 130,000 miles per hour. And what if its path isn't an exit, but a deliberate slowing? What are the odds that a wandering comet could mimic a maneuver with purpose? Tonight, Observer, we follow that possibility through science and shadow, through data and wonder. Stay with me. The discovery of 3I Atlas marks a significant moment in modern astronomy, not because it poses any physical threat to Earth, but because it represents a rare opportunity to examine material from beyond our solar system. First identified as a faint track of motion against the star field, the object's hyperbolic trajectory immediately distinguished it from local solar system bodies. Its orbital eccentricity exceeding 1, 0 identified it as an interstellar visitor, only the third confirmed object of this kind after Sosnoye Oumuamua in 2017 and 2I Borisov in 2019. Initial measurements revealed that 3I Atlas was approaching the Sun at extremely high speed, exceeding 130,000 miles per hour. Its hyperbolic excess velocity of approximately 61 km indicated that this speed would not diminish significantly, even after interaction with the Sun's gravity. Such velocities suggest a long and complex dynamical history involving gravitational encounters with multiple stars across vast timescales. In this sense, 3I Atlas represents not merely a comet, but a physical record of galactic processes spanning millions or even billions of years. Despite public speculation, all risk assessments rapidly converged on the same conclusion. 3I Atlas poses no impact threat to Earth. Its closest approach, approximately 0. 18 astronomical units, around 270 million kilometers, places it at nearly twice the minimum separation of Earth and Mars. Orbital solutions computed by NASA and other agencies confirm that its trajectory is dynamically harmless. Unlike objects on bound elliptical orbits, an interstellar body on a hyperbolic path cannot be captured by solar gravity. It will pass through the solar system once and depart permanently. The scientific interest surrounding 3I Atlas arises from its physical and chemical properties. Early observations from the Hubble Space Telescope showed conventional cometary behavior with solar radiation, sublimating volatile materials and producing a visible coma. However, spectroscopic measurements from the James Webb Space Telescope revealed an unusually high concentration of carbon dioxide relative to water, an extreme CO2 dominant composition not commonly observed in solar system comets. This suggests that the object formed under environmental conditions different from those of our own protoplanetary disk. Such chemical anomalies do not imply artificial origin. Rather, they illustrate the diversity of volatile ratios that can occur across different stellar environments. Models of planet formation predict that cometary bodies, originating in colder CO2-rich regions of protoplanetary disks, should exhibit elevated CO2 to water ratios. Alternatively, long-term cosmic ray exposure or the development of insulating dust mantles could alter surface chemistry over geological timescales. All current data support natural explanations consistent with cometary physics. Ground-based radio and optical observatories have contributed to a global campaign of observation, confirming the absence of artificial signals, unusual accelerations or structural features inconsistent with natural behavior. The object emits only the electromagnetic signatures expected from solar heating of volatile materials. Its trajectory aligns precisely with predictions from gravitational models, with deviations fully attributable to outgassing and radiation pressure. No evidence of controlled propulsion or engineered design has been detected. The broader significance of 3I Atlas lies in its implication for interstellar object frequency. Computer simulations of planetary system formation predict that all young stellar systems eject large quantities of rocky and icy debris through gravitational scattering. If such processes are common, the galaxy should contain a large population of interstellar objects wandering between stars. The recent detections of Oumuamua Borisov and now 3I Atlas may represent the leading edge of a far larger population that improved surveys, especially the upcoming Vera C. Rubin Observatory, are likely to reveal in greater numbers. Chemical diversity among interstellar objects provides insight into the variety of environments in which they formed. The extreme CO2 enrichment of 3I Atlas, while unusual compared to most solar system comets, may be typical of objects formed around certain classes of stars or in early epochs of galactic evolution. Its inferred thick disk origin suggests that it may be billions of years old, potentially older than our solar system. This makes 3I Atlas a unique sample of early galactic material offering clues to the chemistry of ancient stellar populations. The global scientific response has highlighted the strengths of modern astronomy: transparent data sharing, coordinated observations, and rapid communication between institutions. Within days of its discovery, telescopes worldwide were collecting complementary datasets across multiple wavelengths. Space-based platforms such as Hubble and Webb provided high-resolution imaging and spectroscopy, while ground-based observatories contributed photometry, astrometry, and independent confirmation. Despite public fascination with speculative scenarios such as artificial origin or hidden technological systems, there is no empirical support for such claims. The absence of artificial signatures is consistent across all available instruments. While creative speculation can enrich philosophical discussions about extraterrestrial intelligence and the limits of human knowledge, it must remain clearly separated from evidence-based scientific conclusions. The scientific value of 3I Atlas lies not in imagined risks, but in the opportunity to study a physical artifact from another stellar environment. Its passage through our solar system provides insight into chemical processes, dynamical histories, and environmental diversity across the galaxy. By analysing its volatile composition, thermal behaviour, and trajectory, researchers gain direct information about planetary formation beyond the solar system, information unattainable through remote sensing alone. In sum, 3I Atlas represents an astrophysical event of high scientific interest and negligible danger. Its chemical uniqueness, interstellar origin, and extreme antiquity offer a glimpse into the broader galactic ecosystem. As astronomical capabilities improve, such objects will likely become more common in observational catalogues, providing an expanding data set for comparative planetology and galactic evolution. Far from representing a worst-case scenario, 3I Atlas reinforces a reassuring truth even across cosmic distances. And deep time, the laws of physics remain consistent, predictable, and comprehensible. The visitor's silent passage demonstrates that the universe can surprise us without threatening us, challenging our understanding, while affirming our ability to interpret its signals through careful observation and scientific reasoning. The physical character of 3I Atlas becomes clearer when its speed size and likely origin are examined together, not as isolated data points, but as interlocking clues to its long history. Its velocity, the first property to draw astronomers' attention, is extraordinarily high even by the standards of long-period comets, travelling inward at more than 130,000 miles per hour and carrying a hyperbolic excess velocity of about 61 km/s. The object cannot be a native of the solar system. Such speed is neither mysterious nor unprecedented. It is the natural outcome of gravitational interactions accumulated over immense spans of time. Early in a planetary system's development, giant planets scatter countless icy bodies outward through repeated encounters, and many of those fragments eventually acquire enough kinetic energy to escape the gravitational influence of their host star. Once freed, these objects wander through interstellar space, collecting additional accelerations from the random gravitational fields of stars they pass near. 3I Atlas likely followed such a path. Its extreme speed therefore offers insight into the dynamical processes that shape other planetary systems just as they shaped our own. Estimating the size of the object, however, proves far more difficult. The visible coma masks the nucleus so thoroughly that direct measurement remains uncertain. Current estimates place the nucleus somewhere between a few hundred meters and several kilometers in diameter, a range wide enough to invite speculation, but narrow enough to remain scientifically useful. Regardless of its exact size, the very fact that the body survived ejection from its natal system, endured the hazards of interstellar space and remained intact, long enough to reach our solar system, indicates that it must be relatively robust. small fragile objects would not have survived the violent gravitational encounters required to accelerate them to such speeds. Nor would they have tolerated the long-term exposure to cosmic radiation, micrometeoroid impacts and thermal extremes inherent to interstellar travel. In this sense, the survival of 3 Atlas is consistent with theoretical expectations about the durability of planetesimals scattered from developing planetary systems. The most scientifically provocative property of 3I Atlas is not its speed or size, but its likely origin. Modelling of its motion through the galaxy suggests that it may belong to the Milky Way's thick disk, a population of stars older than the Sun and formed under very different conditions. If this interpretation is correct, the object predates our solar system by billions of years and carries chemical signatures reflecting environmental conditions that no longer exist in the galaxy. This possibility transforms 3I Atlas into more than a wandering comet. It becomes a tangible relic of early galactic history. Its unusual chemical composition, particularly its high carbon dioxide abundance relative to water, may illustrate the diversity of volatile inventories in the early galaxy. It may reflect formation around a colder or more carbon-rich star, or the cumulative effects of cosmic ray processing over geological timescales. Such explanations are entirely natural and require no extraordinary assumptions. Rather, they highlight how interstellar objects can serve as unique samples of ancient environments far removed from our own. Despite its exotic origin and impressive velocity, the trajectory of 3I Atlas poses no danger to Earth. Its hyperbolic orbit ensures that it will not be captured by the Sun, and its minimum distance from Earth, approximately 270 million kilometers, completely eliminates any possibility of collision. Observed deviations from purely gravitational motion are consistent with ordinary outgassing forces and solar radiation pressure, both well understood in cometary physics. Nothing in its behavior implies artificial influence or controlled propulsion. Its path through the solar system follows the same principles that govern every natural body subjected to gravity and heating by the Sun. The deeper question raised by 3I Atlas is not whether it poses a threat, but what its existence implies about the broader structure of the galaxy. If 3 interstellar objects have been detected within a span of less than a decade, it becomes increasingly likely that these visitors are far more common than previously assumed. Simulations of early planetary formation already predict that stellar systems should eject enormous numbers of small bodies into interstellar space. The discovery of 3I Atlas, alongside its predecessors, provides empirical support for this view. As observational technologies improve, most notably with the arrival of the Vera C. Rubin Observatory, astronomers may soon detect such objects routinely. This expanding catalogue will allow researchers to map the chemical diversity, dynamical histories and formation environments of objects born around other stars in ways that were impossible only a generation ago. In this light, the so-called worst-case scenario associated with 3I Atlas dissolves upon examination. There is no physical threat and no evidence of artificial origin. Instead, the object challenges our assumptions about planetary formation, volatile chemistry, and the diversity of environments that shape bodies across the galaxy. The only real danger, if it can be called that, is philosophical. The realization that our solar system represents just one example within a vast and varied galactic ecosystem. 3 Atlas reminds us that the processes shaping worlds elsewhere do not necessarily resemble the processes that shaped our own. It underscores how little we know about the environments in which other stars formed their planets and how many mysteries remain unresolved at galactic scale. Ultimately, the passage of 3I Atlas offers an extraordinary scientific opportunity. It brings to our doorstep a fragment of ancient interstellar material, shaped by forces and conditions far beyond the reach of any probe we could launch today. Its behavior affirms the predictive power of classical celestial mechanics, while its chemistry expands our understanding of the galaxy's formative epochs. Far from representing a threat, it demonstrates the stability and comprehensibility of natural laws across deep time and vast distances. What it reveals is not danger but perspective, and in that sense its arrival may be one of the most scientifically valuable events of our generation. The chemical composition of 3I Atlas introduces an additional layer of complexity that deepens the scientific intrigue surrounding this interstellar visitor. When the James Webb Space Telescope captured its infrared spectrum, the results were immediately recognised as unusual. Unlike most comets originating from the solar system, where water vapour typically dominates the coma, 3I Atlas exhibited an exceptionally high ratio of carbon dioxide to water, one of the most extreme CO2 dominant signatures ever measured in a comet-like object. This anomaly does not suggest anything artificial or technological. Rather, it indicates that the object formed in a region of its original protoplanetary disk, with environmental conditions very different from those near the Sun when our solar system developed. The abundance of carbon dioxide may reflect formation close to the CO2 snowline around a colder star or in an environment where water ice was less prevalent. Alternatively, the object's surface may have undergone extensive cosmic ray processing over geological timescales, altering the top layer so significantly that CO2 sublimates more readily than water during solar heating. These explanations demonstrate how chemical diversity among interstellar objects can expand our understanding of how different planetary systems evolve. It is important to emphasize that such chemical outliers are not without precedent. Comet C 2016 R2. Pan-STARRS, for example, displayed unusual concentrations of carbon monoxide and nitrogen compounds, reminding researchers that the chemistry of icy bodies is shaped by a wide range of initial conditions and evolutionary paths. In this context, 3I Atlas becomes another data point illustrating the breadth of chemical possibilities in planetary formation. The fact that its chemical profile deviates from what is typical in the solar system should not be interpreted as evidence of artificial manipulation. Instead, it highlights how limited our perspective remains. For most of human history, we had direct access only to objects formed around our own sun. Interstellar visitors like 3 Atlas offer the first real opportunity to compare our solar system's chemistry with that of extraterrestrial systems using physical samples, even if those samples arrive only in the form of vaporized molecules drifting from a distant nucleus. Observations from ground-based telescopes complement Webb's findings, confirming that the emissions detected are consistent with natural cometary activity. Radio telescopes listening for structured or coherent electromagnetic signals, a hallmark of technological origin, found only the broad, unpatterned emissions produced by natural interactions between solar radiation and comet material. No narrow-band radio transmissions, no modulated signals, and no artificial spectral lines have been detected. Instruments sensitive to heat signatures observed temperatures entirely expected from an object heated by solar radiation. The coma expands and brightens with increasing solar proximity, exactly as predicted for an icy nucleus with volatile materials near its surface. Even the object's rotation-driven brightness variations follow a familiar pattern comparable to those observed in other comets, whose shape, surface irregularities and jet activity cause periodic fluctuations in reflected sunlight. Despite intense public speculation, there is simply no observational evidence supporting ideas of propulsion steering or controlled motion. If 3I Atlas contained any mechanism capable of directional thrust, however subtle, it would manifest as non-gravitational accelerations that diverge from outgassing models. Instead, its trajectory remains consistent with the typical forces experienced by comets, gravitational attraction from the Sun, minor perturbations from planets, and the reactive force of sublimating gases. Each observed deviation aligns with predictable physical causes. Nature, not engineering, explains the data. What makes the object compelling is not any apparent violation of natural laws, but rather how it reinforces them while simultaneously pushing against the boundaries of our knowledge. Its chemical composition challenges the assumption that water-rich comets are universal. Its speed demonstrates how dynamic and chaotic planetary systems can be. Its likely origin in the Milky Way's thick disk connects us directly to epochs long before Earth existed. These features invite reflection on the diversity of environments that shape the galaxy's earliest generations of stars and planets. For researchers, the object represents an opportunity to test models of planetary formation against physical evidence gathered far beyond our solar system. For the broader scientific community, it stands as a reminder that our current understanding, while sophisticated, still represents only a narrow view of the galaxy's complexity. Even the object's temporary disappearance behind the Sun during its perihelion passage underscores the natural limitations of observational astronomy. When 3 Atlas entered the region of intense solar glare in late 2025, all telescopic monitoring from Earth became impossible. This is a predictable reality dictated by geometry, not an engineered tactic. Objects near the Sun simply fall into regions of the sky where no Earth-based instrument, optical or radio, can safely point. Yet this unavoidable gap in observation has fueled speculation precisely because it coincided with the moment of greatest solar heating, when the comet's activity might increase. Scientific patience, however, depends on recognizing that such observational blind spots are an inherent part of astronomical research. Once the object emerges again, instruments will resume their work gathering the data needed to refine models and improve understanding. Ultimately, the chemical and observational profile of 3I Atlas enriches our view of the galaxy without contradicting established scientific principles. Everything observed thus far fits within the broad but coherent spectrum of natural cometary behaviour, albeit with characteristics that expand known boundaries. The object reminds us that our solar system is not the template for the universe, but merely one example among countless variations shaped by conditions we are only beginning to explore. It affirms the importance of maintaining a careful balance between curiosity and skepticism, imagination and evidence. And above all, it illustrates that every interstellar visitor, no matter how unusual, offers a chance to revise, refine and expand the models through which we understand the cosmos. As 3 Atlas moved deeper into the inner solar system, attention turned to the series of coordinated observations planned around its close approach to Mars. This moment represented a rare scientific opportunity, not because the object posed any threat to the planet, but because Mars serves as an observational platform equipped with instruments that could capture the visitor from a unique vantage point. Orbital cameras such as HiRISE CASes and the Mars Express imaging systems were positioned to record data during the period when 3I Atlas passed approximately 29 million kilometers from the Martian orbit. Although this distance is substantial, it is close enough that the high-resolution cameras normally used to resolve meter-scale features on the Martian surface could at least detect the brightness profile of the interstellar object, and potentially provide indirect constraints on the size of its nucleus. In theory, such coordinated imaging could refine estimates of the object's shape rotation period, outgassing activity and coma structure. Yet the data release did not occur as rapidly as the public anticipated. When NASA and ESA released no immediate imagery, speculation grew rapidly across online communities. The absence of instant results, though completely consistent with standard processing timelines, was interpreted by many as a sign that the agencies had observed something extraordinary. In reality, delays in processing are entirely normal. Raw data must be calibrated, geometrically corrected, filtered for noise, and reviewed before being released through public archives. When the target is faint distant and moving against a field of stars, the process becomes even more time-intensive, requiring specialized detection algorithms to distinguish the desired signal from background noise. The gap between observation and publication therefore reflects internal workflow rather than the content of the images themselves. Observers familiar with Mars data pipelines recognize that days or even weeks can pass before high-quality products become accessible. Despite this, the silence surrounding the initial Mars observations illustrates how scientific uncertainty can become fertile ground for speculation. Amateur astronomers examining open-access rover images believed they detected faint moving points, interpreting them as signs of multiple objects accompanying 3I Atlas. While these analyses demonstrate admirable enthusiasm and technical skill, their conclusions do not withstand statistical scrutiny. Rover cameras have limited sensitivity to faint celestial sources, and long exposure stacking of images easily produces artifacts that resemble motion. Subtle variations in atmospheric scattering on Mars starfield alignment errors or cosmic ray hits on camera sensors can imitate small streaks of light. Without corroboration from independent instruments, such features cannot be considered evidence of companion objects. The scientific method requires repeatability, cross-verification, and careful calibration standards that individual rover frames simply cannot meet. Nevertheless, the public fascination generated by these ambiguous detections highlights an important sociological dimension of interstellar object research. Events like the Mars flyby occur at the intersection of public curiosity, limited data availability, and the inherent mysteries of astronomical phenomena. Modern astronomy operates transparently with many datasets released in near real time. This openness encourages meaningful public engagement, but it also exposes unprocessed data to misinterpretation. Enthusiastic observers equipped with powerful image processing tools but often lacking the full context of observational limitations sometimes draw conclusions that deviate from scientific consensus. Such interpretations proliferate online because they offer compelling narratives that blend wonder with uncertainty. The scientific community, by contrast, proceeds cautiously. Researchers emphasize that extraordinary claims require extraordinary evidence, and no such evidence has emerged. Every observational anomaly attributed to 3I Atlas thus far has found conventional explanations consistent with known physics, outgassing, effects, thermal evolution, observational geometry, processing artifacts, and statistical noise. This does not diminish the object's scientific value. Rather, it situates it firmly within the domain of natural astrophysical processes. The Mars data, once fully released, will likely refine current estimates, but not overturn the foundational conclusion that 3I Atlas is a naturally formed interstellar comet undergoing typical interactions with solar radiation. This tension between public speculation and scientific caution reveals something deeper about how humanity responds to cosmic uncertainty. Interstellar visitors disrupt the familiar frameworks through which people understand the sky. Unlike planets and periodic comets, which follow predictable cycles, objects like 3I Atlas arrive unexpectedly, carry unfamiliar chemical signatures, and depart forever after a brief passage. They embody transience and otherness, characteristics that naturally invite both scientific inquiry and imaginative interpretation. The human mind gravitates toward meaning pattern and narrative, particularly when confronted with phenomena that resist immediate classification. But meaning must be pursued with discipline, otherwise curiosity becomes conjecture. In this context, 3I Atlas functions as a mirror, reflecting humanity's relationship with the unknown. For scientists, it is a valuable data point in the emerging field of interstellar object research, a sample of ancient galactic material that can refine models of planetary formation and chemical diversity. For the public, it becomes a symbol of mystery, sometimes projected with fears, hopes, or speculative narratives. Neither reaction is inherently misguided. Rather, they illustrate two different modes of engagement with the cosmos, one grounded in empirical methodology, the other in existential curiosity. When balanced, they enrich one another. When conflated, they generate confusion. As the object continues its journey approaching perihelion, an eventual departure from the solar system, the data gathered will gradually replace uncertainty with clarity. Models will sharpen, spectroscopic readings will be interpreted more precisely, and high-resolution imaging may reveal structural or compositional details still unknown. The scientific process is often slow, but its strength lies precisely in this deliberate pace. Each new dataset becomes a piece of a larger mosaic, contributing incrementally to an increasingly accurate understanding of the object. In this way, 3I Atlas becomes not a source of alarm but an opportunity, a moment when a fragment of distant cosmic history passes close enough for careful measurement and thoughtful interpretation. As additional data from ground-based observatories accumulated, a clearer picture of 3I Atlas began to emerge, one shaped not by sensational anomalies, but by the subtle interplay of physics, chemistry, and long baseline astronomical observation. The comet's coma brightened in accordance with its decreasing heliocentric distance, following thermal models that predict enhanced sublimation as solar radiation penetrates subsurface layers. Even the unexpectedly high carbon dioxide content, which initially raised eyebrows, fits within broader theoretical frameworks once the object's likely formation environment is considered. Galactic thick disk regions with their older stellar populations and distinct chemical abundances can produce icy bodies with volatile ratios markedly different from those found in our own solar system. Thus, the unusual composition of 3I Atlas may not represent a contradiction of known chemistry but an expansion of it, a reminder that planetary formation processes are not uniform across the Milky Way. This expanding dataset allowed astronomers to begin treating 3I Atlas not as a singular anomaly, but as part of a potential population of chemically diverse interstellar objects. The precedent set by Oumuamua and 2I Borisov already suggested a wider distribution of cometary behaviours and compositions than previously expected. With 3I Atlas, the trend toward diversity becomes even more apparent. Each new interstellar visitor challenges assumptions built upon a sample size of our own solar system. When objects from other stellar nurseries appear, they carry with them the chemical imprints of environments we cannot directly observe. Their volatile ratios, isotopic signatures, and thermal responses become proxies for distant protoplanetary disks, effectively extending our observational reach across both space and time. Yet while these scientific implications are profound, the public discourse surrounding 3I Atlas has often been more concerned with symbolic meaning than chemical details. The delay in releasing Mars flyby imagery fed speculative narratives that overshadowed the more mundane truth the processing pipeline requires time, human review, and calibration. The absence of images became in some circles evidence of intentional withholding rather than simple logistical delay. This pattern reflects a broader cultural phenomenon. In an era when information flows continuously and instantaneously, any pause or gap becomes a vacuum into which speculation readily expands. Scientific institutions, by contrast, still operate on timescales, optimized for accuracy rather than immediacy. This mismatch generates tension that becomes visible whenever public fascination intersects with complex scientific workflows. Even so, it is worth acknowledging the emotional undercurrent beneath these public reactions. Interstellar objects carry a psychological weight disproportionate to their physical characteristics. Their origins are unknown, their trajectories unrepeatable, and their presence fleeting. They arrive without warning and depart without return. In a universe filled with cycles, seasons, orbits, planetary rotations, these objects break the pattern. They are visitors from outside the familiar gravitational rhythms that define human experience. For many people, this unfamiliarity evokes unease, curiosity, or existential reflection. The absence of information becomes amplified not because the information itself is urgent, but because the object represents the unfamiliar in its purest form, something that does not belong to our solar system yet briefly enters it. Scientists recognize this emotional dimension even if they do not typically address it explicitly. The empirical method relies on dispassionate analysis, yet the human mind does not. When data gaps appear, the imagination fills them with concerns that draw upon the long cultural history of comets as omens, messengers, or symbols of change. Modern scientific literacy has tempered these reactions, but traces remain shaping how non-specialists interpret astronomical events. Interstellar objects with their dramatic trajectories and alien origins tap into these ancient narratives even as they serve modern, scientific objectives. The reality, however, remains grounded in physics. No evidence suggests that 3I Atlas behaves inconsistently with natural cometary dynamics. Its trajectory matches predictions derived from gravitational models. Its non-gravitational accelerations fall within the expected range for CO2-driven sublimation. Its brightness fluctuations correlate with rotational modulation and dust release. Even the faint emissions detected by radio telescopes align with expected thermal and electromagnetic signatures. When ambiguous features appear, faint streaks, unexpected sparkles, or minor irregularities, they find natural explanations once instrumental noise processing artifacts or observational geometry are accounted for. This process, moving from initial mystery to refined understanding, beautifully illustrates the scientific method. Hypotheses form quickly in the presence of uncertainty, but they evolve or disappear as evidence accumulates. Over time, the extraordinary becomes understandable, the unknown becomes familiar, and the sensational becomes simply another data point within a growing body of knowledge. It is not disappointment that follows this transformation, but clarity. The refinement of understanding is itself a form of discovery, demonstrating that the universe remains coherent, even when individual phenomena appear strange at first encounter. As researchers continue to model the comet's thermal behaviour, they identified subtle patterns suggesting layered sublimation dynamics. The dominance of carbon dioxide at large heliocentric distances implies a surface or near-surface enrichment, possibly the result of long-term radiation processing that depleted more volatile water molecules from the outer layers. Deeper beneath the surface, water ice likely persists, awaiting the perihelion, induced heating required for activation. Should later observations detect a shift in dominant emissions from CO2 to H2O, it would confirm this layered structure and refine models of the object's thermal history. Such results would hold significance far beyond 3I Atlas itself, offering insights into how interstellar radiation fields shape icy bodies over billions of years. The significance of this lies not only in the object's chemistry, but in its longevity. To survive ejection from its parent system, endure countless micrometeoroid impacts, and persist through the irradiation hazards of interstellar travel requires structural resilience. The survival of such objects demonstrates that the galaxy is not only filled with dust and gas, but with intact remnants of planetary formation fragments that have witnessed epochs older than the Earth itself. Studying these remnants allows humanity to glimpse the early chemical conditions of stellar systems that no longer exist, effectively extending the reach of observational astronomy into eras long erased by cosmic evolution. In this way, 3I Atlas becomes more than a visitor. It becomes a messenger of ancient galactic history. Its structure, composition, and behaviour are chapters of a story written before the Sun existed. The scientific task is not to interpret it as an anomaly, but to read it as a primary text from a distant Epoch 1 that speaks through chemistry, dynamics, and spectral lines rather than language. And as each new observation refines its story, uncertainty diminishes, giving way to a fuller picture of the processes that govern planetary formation across the Milky Way. As the observational campaign expanded, astronomers began to place 3I Atlas not only in the context of interstellar chemistry, but also within the broader statistical architecture of galactic debris. Theoretical models have long predicted that every planetary system ejects vast quantities of rocky and icy material during its early evolution. Most of these fragments remain gravitationally bound to their parent stars, but a significant minority nudged by giant planets' resonances or close stellar encounters escape, entirely becoming long-term wanderers drifting between stars. Until recently, these objects were purely theoretical, but the detections of Oumuamua, Borisov, and now 3I Atlas demonstrate that such wanderers not only exist, but pass through our solar system often enough to be detected by modern survey telescopes. This shift from theoretical expectation to empirical confirmation has profound implications. It suggests that the Milky Way is populated by a vast invisible stream of these objects, each carrying chemical signatures from its place of origin. The diversity already observed from Borisov's unusually pristine composition to 3I Atlas's CO2 dominance implies that planetary systems across the galaxy may differ from one another far more dramatically than once assumed. In this sense, 3I Atlas is not an outlier, but a data point within a distribution we are only beginning to map. Future discoveries will likely reveal compositions and behaviours that surpass even the unusual chemistry seen here. This view reframes the object's significance. Rather than treating its unusual properties as evidence of something unnatural, the diversity strengthens the argument for a vast and varied galactic ecosystem of icy bodies shaped by different stellar environments, radiation fields, and material abundances. These objects then become essential for reconstructing the galactic fossil record, the chemical and dynamical history of systems that may have long since transformed or vanished. By studying them, astronomers effectively probe the early conditions of distant stars without ever leaving the solar system. Yet despite this emerging clarity, public fascination continues to orbit around hypothetical scenarios that diverge from scientific consensus. When an object arrives from outside the solar system, the human imagination naturally gravitates toward the extraordinary. This is neither irrational nor surprising. Humans evolved to interpret and respond to anomalies as potential threats or opportunities. In the modern era, these instincts manifest not as physical reactions, but as interpretive frameworks, stories, assumptions, anxieties, and speculations. In the case of 3i Atlas, much of this public speculation centres on the notion of deliberate design or hidden purpose. Some wonder whether its unusual composition might represent a kind of signature, as though chemistry itself could encode intention. Others focus on its immense speed or ancient origin, imagining scenarios in which technology, rather than natural processes, carries such an object across the galaxy. These narratives often flourish in the space between preliminary data and refined analyses, filling gaps with possibility. But the scientific response remains grounded in evidence. When spectroscopic anomalies appear, researchers seek natural explanations. When brightness fluctuations occur, they examine rotation periods, outgassing patterns or dust dynamics. When orbital deviations arise, they compare them against sublimation-driven forces, not hypothetical propulsion. This disciplined approach is not a rejection of imagination, but a structure that ensures imagination does not replace evidence. The scientific method does not diminish wonder, it preserves it by ensuring that mystery is not confused with misunderstanding. This distinction becomes even more important given the increasing complexity of modern astronomical instrumentation. Telescopes like Webb and Hubble generate data that require careful calibration and processing, often revealing features that look artificial to the untrained eye. Diffraction spikes, cosmic rays, sensor noise, and processing artifacts can simulate patterns or anomalies that appear meaningful, but ultimately reflect the nature of the instrument rather than the object being observed. Scientists navigate these pitfalls through methodology. The public lacking such training frequently mistakes artifact for signal. The remedy is not dismissal, but explanation, an ongoing effort to bridge the gap between perception and understanding. It is within this interplay between public curiosity and scientific rigour that 3i Atlas finds its cultural significance. The object becomes a mirror in which humanity projects both its anxieties and aspirations. We wonder whether we are alone. We imagine ancient intelligences. We ask whether the universe has ever noticed us. These questions, while not grounded in the specifics of 3i Atlas itself, are nevertheless awakened by its presence. In this way, interstellar visitors function as catalysts for reflection, even when the scientific narrative remains strictly natural. Meanwhile, the object's physical reality continues its quiet journey. As it approaches, perihelion models predict a shift in coma composition, as subsurface layers heat and new volatiles activate. If water ice begins to dominate emissions, it will confirm theoretical stratification models. If CO2 continues to dominate, it will deepen the mystery of its formation environment. But in either case, the outcome will refine our understanding of how icy bodies respond to long-term exposure in interstellar space. These results will feed into broader theoretical frameworks that inform models of planetary formation, volatile distribution, and galactic evolution. The comet's survival itself is a testament to the resilience of icy bodies shaped by other suns. Interstellar radiation gradually modifies surfaces, but deeper layers remain protected. Impacts scar or fracture the nucleus, but rarely destroy it. Gravity molds its path, but does not erase its identity. The object becomes an archive, an unintentional repository of chemical memory spanning billions of years. Understanding such memory allows astronomers to reconstruct conditions that no longer exist, much as paleontologists infer ancient ecosystems from fossilized remains. In a sense, 3i Atlas is a fossil too, one that drifted alone through the galaxy until our instruments briefly intercepted it. As the comet moves through the inner solar system, its behaviour remains consistent with physical laws that have governed celestial dynamics since the universe's youth. The predictability of its motion is not merely a mathematical achievement, but a philosophical reminder even objects from distant systems obey the same fundamental principles. This uniformity transforms the galaxy from a collection of isolated systems into a unified physical domain where gravity, chemistry, and radiation follow the same rules everywhere. It is this unity, not exotic speculation, that makes the cosmos extraordinary. The continued study of 3i Atlas thus serves two parallel purposes. It satisfies scientific curiosity through data analysis and theory, and it satisfies a deeper human need to confront the vastness of our context, to situate ourselves within a universe that is neither hostile nor benevolent, but indifferent and magnificent. understanding dispels fear, but it also deepens wonder, revealing a cosmos governed by laws that are knowable, yet filled with phenomena that remain unexplored. The comet will leave our solar system just as it entered, quietly, predictably, and without fanfare. The images and spectra it leaves behind will become part of the scientific record informing future models and comparisons. The object itself will return to the interstellar medium, continuing a journey that began long before humanity existed. Whether it ever encounters another star system is unknown. The galaxy is vast and most interstellar wanderers drift for eons without interacting with any planetary body. But its brief passage through our system marks a moment in which human observation intersected with ancient cosmic motion. A crossing of trajectories between a species still in its infancy and an object shaped by epochs beyond imagination. In that intersection lies the true value of 3i Atlas, a chance to measure, to learn to reflect, and to remember that the universe is larger, older, and more varied than our limited experience can fully comprehend. As observational certainty grew, scientists turned their attention from the comet's origin and chemistry to the broader philosophical implications of encountering yet another interstellar visitor, whose strangeness dissolves piece by piece under the scrutiny of data. In doing so, a deeper truth emerged: the tension between imagination and evidence is not a flaw in human inquiry, but a feature of it. Our species has always oscillated between wonder and explanation, between mythic interpretation and empirical understanding. Interstellar objects simply amplify this tendency because they embody the unknown in its purest form, arriving unannounced, following no periodic cycle, bearing no allegiance to the sun that governs our familiar celestial patterns. For astronomers, this oscillation presents both an opportunity and a challenge. On one hand, public fascination fuels support for the observatories and missions that make discoveries like 3i Atlas possible. On the other, the same fascination can drift into narratives that obscure rather than illuminate, driven not by malice, but by a human instinct to make meaning out of mystery. Yet the scientific method by design remains indifferent to narrative. It proceeds through measurement, repetition, correction, and incremental refinement. And as the weeks passed, each refinement reaffirmed the natural origin of this object. The absence of artificial signals, radio-optical, thermal, was not merely reassuring, it was predictable. The physics of interstellar travel, though often treated as a frontier for speculation, imposes strict limitations that any engineered probe would struggle to overcome. Radiation exposure accumulates inexorably over millions and billions of years, degrading materials, erasing circuits, corrupting stored data, and weakening structural integrity. The very conditions that allow simple icy bodies to persist low density, low structural complexity, passive thermal behavior, are precisely the conditions that sabotage complex machinery. In this way, 3i or Atlas's simplicity is not suspicious, it is necessary. Likewise, its trajectory reflects nothing beyond gravitational influence and outgassing physics. If the object had been capable of deliberate propulsion or course adjustment, the signs would have been unambiguous deviations not correlated with solar heating, thrust signatures inconsistent with sublimation, or rotation patterns showing controlled stabilization. None were observed. Instead, its motion aligned perfectly with models that treat it as a passive mass responding to the universal forces acting upon it. This alignment, sometimes dismissed as mundane, is in fact remarkable, not because it eliminates extraordinary hypotheses, but because it connects an alien object to physical principles that apply everywhere in the cosmos. Even the object's unusual CO2-dominated coma, while initially dramatic fits within natural chemical pathways. Radiation processing over deep time can preferentially erode water molecules, leaving carbon dioxide trapped beneath insulating layers that gradually break apart as the object nears the sun. If anything, 3i Atlas teaches scientists that cometary chemistry may be more variable than are previously assumed, shaped not only by formation environment, but also by the cumulative effect of its multi-billion-year journey through interstellar space. In this sense, the comet is less a mystery to be solved and more a data point that widens the known range of cosmic conditions. Yet in parallel with these scientific interpretations, another quieter realization grew among researchers. The significance of 3i Atlas is not determined by what it is, but by what it represents. Its age, likely older than the solar system, implies that it began its journey before Earth formed oceans or atmospheres. Its velocity suggests countless gravitational encounters, each imparting a small push, collectively accelerating it to the speed at which it now crosses our celestial neighbourhood. Its chemistry reflects processes that occurred in stellar regions humanity may never directly observe. These features transform the comet into a kind of time capsule, carrying material imprints of a galaxy that existed in a different era. This realization brings with it a sense of humility. For all our technological progress, the instruments that study 3I Atlas represent only the tiniest fraction of human history. Our entire scientific tradition from Newton to Webb occupies a sliver of time compared to the object's ancient odyssey. And yet, through those instruments, we can decode its composition, track its motion, and extrapolate its origins. This juxtaposition, our youth as a species versus our growing reach as observers, illustrates the fragility and ambition of human inquiry. The cultural impact of this juxtaposition is equally significant. Many people interpret interstellar visitors not merely as scientific phenomena, but as reminders of cosmic scale. Their presence implicitly raises existential questions. Why are we here? How typical is our world? How many other systems formed, evolved, and vanished before our planet even existed? These questions are not answered by spectroscopy or orbit modelling, yet they are evoked by them. The comet's silence becomes symbolic not of emptiness, but of the vast unobserved history that precedes us. In this way, 3I Atlas embodies a paradox. The more precisely we measure it, the more deeply it evokes feelings that transcend measurement. The object becomes both a scientific specimen and a philosophical mirror. Its chemical ratios inform models of planetary formation. Its age inspires reflections on human transience. Its trajectory demonstrates celestial mechanics. Its origin provokes wonder about the long-vanished stars that may have shaped it. As the comet approached perihelion, researchers anticipated changes in brightness, coma expansion, and outgassing behaviour. These changes were expected not as surprises but as confirmations of thermal evolution models. Yet even this predictability reinforced the object's significance, offering further evidence that natural processes operate consistently across vast gulfs of time and space. The comet's response to sunlight near perihelion echoed the behaviour of comets bound to our own sun despite their radically different histories. This symmetry underscores a unifying truth: the universe is governed by laws that bridge the familiar and the alien, the ancient and the immediate. As its orbit carried it around the sun and back toward the outer solar system, attention began shifting from observation to synthesis. The datasets collected spectra-like curves, astrometric measurements, thermal models would shape research for years to come. Already early papers discussed implications for comet formation in low metallicity environments and possible refinements to models of volatile retention in interstellar bodies. Some researchers focused on the object's significance for galactic chemical mapping. Others viewed it as evidence supporting simulations of high-velocity ejection events in planetary systems. In each case, 3I Atlas functioned not as a puzzle, but as a key unlocking new directions of inquiry, and when the comet finally fades beyond the reach of our most sensitive instruments, its influence will remain not as a source of anxiety or speculation, but as a milestone in the ongoing effort to understand the galaxy through the messages carried by its wandering remnants. In that sense, wonder and logic converge. The object does not require exotic explanation to be extraordinary. It only requires recognition that its existence is itself a testament to the richness and complexity of the Milky Way. Nothing about it is mundane, even when everything about it is natural. The deeper the scientific community delved into the behaviour of 3I Atlas, the clearer it became that its greatest contribution lay not in any single measurement, but in the collective structure of evidence it forced humanity to assemble. By coordinating global observations ranging from professional observatories in Chile, Hawaii, and the Canary Islands, to university instruments and amateur telescopes, astronomers constructed a multi-layered portrait of the object that represented modern science at its most collaborative. Every dataset, no matter how small, fed into orbital refinements or chemical models that sharpened the overall picture. In this way, 3I Atlas transformed from a solitary wanderer into a shared intellectual project. A reminder that knowledge becomes meaningful only when verified, challenged, and refined by many minds working in parallel. As its trajectory took it closer to the sun's solar glare gradually obscured direct observation, for several weeks the object passed behind the overwhelming brightness of the inner heliosphere, rendering ground-based observations nearly impossible. This temporary disappearance, far from a cause for suspicion, reflected the geometry of its orbit, an unavoidable interval when the sun's luminosity simply overwhelmed the faint light reflected by the comet. In earlier centuries, such disappearances inspired fear or myth. Comets vanishing into the sun were seen as omens extinguished in celestial fire. Today, the disappearance was a matter of prediction. The object had moved behind the sun. Its orbit guaranteed it would re-emerge. Nothing mysterious lay in the gap, only physics operating with quiet reliability. When it reappeared, its brightness had evolved exactly as models predicted. Sublimation rates increased as deeper volatiles reached activation temperatures. Dust production surged briefly as the nucleus shed accumulated layers of processed material. Spectral signatures shifted in wavelength intensity ratios corresponding to temperature changes, consistent with increasing solar proximity. Every change matched expectations of thermally driven behavior. If anything, the comet's predictability reinforced how effectively physical models capture the dynamics of bodies shaped by solar radiation. The routine of this reappearance was itself remarkable. Humanity had tracked an object that originated around another star-crossed interstellar space for untold ages, slipped behind our sun, and then emerged in the exact location predicted by celestial mechanics. The confidence embedded in these predictions, the ability to forecast the motion of an alien object months or years in advance, reflects not only astronomical skill, but the profound universality of gravitational laws. In a galaxy measured in trillions of kilometers, predictability is more awe-inspiring than anomaly. Yet alongside this scientific triumph, a quieter human realization settled in. Even when an interstellar object aligns with known physics, it still carries emotional weight simply because of what it represents. Objects like 3I Atlas are reminders that our solar system is not an isolated bubble, but a permeable node in a dynamic galactic environment. Material from distant stars can and does enter our neighborhood. Planetary systems are not static. They are porous, exchanging debris across immense distances and timeframes. The idea that fragments of unknown worlds drift past our sun is inherently humbling. It dissolves the illusion of cosmic boundaries and underscores the interconnectedness of stellar evolution across the Milky Way. This interconnectedness also clarifies why extraordinary explanations are unnecessary. Nature itself provides mechanisms capable of producing objects of tremendous diversity and complexity. Star systems eject material through gravitational instabilities, planetary migrations, and close encounters. Radiation fields sculpt chemical compositions. Collisions fracture objects into smaller bodies, more capable of surviving interstellar conditions. Over millions of years, these fragments drift outward, shaped by nothing but time radiation and the occasional gravitational nudge. That one such fragment happened to intersect human observation does not require destiny or design. It requires only the vastness of the galaxy and the persistence of natural processes. The more data researchers collected, the more instructive this naturalness became. By mid-mission, astronomers had compiled a detailed timeline of the comet's activity, initial CO2 dominance, slow coma growth, rotational modulation, consistent with the diffuse nucleus minor fragmentation events, characteristic of thermal stress and gradual dimming after perihelion. Each stage provided direct insights into the chemistry and structure of interstellar ices. These insights fed back into models of early solar system formation, because comparing local cometary behavior to interstellar behavior reveals how environment shapes composition. In effect, the comet served as a control variable, a comparison point that helped calibrate models of our own system's early history. Even planetary scientists, whose work typically focuses on local objects, found value in the interstellar visitor. Volatile ratios help constrain the temperature gradients present in ancient disks. Dust grain mineralogy reveals details about condensation sequences. isotopic fingerprinting, though limited by observational resolution, suggests which nuclear processes dominated the star around which the object originally formed. These clues extend our knowledge beyond what telescopes alone can infer from starlight. While the object itself remains distant and inaccessible, its electromagnetic signatures extend our reach into environments we cannot travel to. Amid these scientific gains, discussions in astrobiology grew more nuanced. Although no evidence of biological processes existed in 3I Atlas, its mere presence raised questions about how frequently material is exchanged between stellar systems. If icy bodies routinely traverse interstellar distances, then chemical building blocks, amino acid precursors, organic molecules, and other carbon-bearing compounds may also circulate throughout the galaxy. This does not imply panspermia in the literal sense, but it does imply that ingredients for prebiotic chemistry are not isolated phenomena. Instead, they may be distributed across the Milky Way through billions of comet-sized couriers, each carrying a unique blend of volatiles shaped by its birthplace. In this context, 3I Atlas becomes part of a larger story about the distribution of life's raw materials. Its passage also highlighted the delicate relationship between precision and uncertainty in scientific communication. Researchers must convey the boundaries of knowledge without overstating them, acknowledging what is known while marking where interpretation begins. This balance was evident in every press release, scientific publication, and public statement. NASA and ESA presented the object as both remarkable and harmless, unusual but not alarming, informative but not transformative. This restraint prevented speculation from outrunning evidence and preserved public trust in the scientific process. Yet the restraint did not diminish the wonder. Instead, it grounded wonder in reality, demonstrating that the universe does not need embellishment to be astonishing. A natural object older than Earth, passing quietly through the solar system, is profound enough. Its chemical history tells stories older than the Sun. Its dynamical path traces gravitational interactions across unimaginable distances. Its survival reveals the durability of icy worlds shaped in alien environments. And its silence, the absence of artificial signals or anomalous behaviour, is its own message, reminding us that the universe's strangeness does not require intent. By the time 3I Atlas began its outbound path toward the outer solar system, the scientific community had already extracted most of the data it would ever provide. Additional observations would refine models, but would not fundamentally change the picture. The object taught exactly what it was capable of teaching: that the galaxy is filled with wanderers, that planetary formation is chemically diverse, that interstellar travel, when driven by nature rather than technology, is an inevitable consequence of gravitational dynamics, and that humanity remains a young observer in a cosmos filled with ancient travellers. In the end, the significance of 3I Atlas lies not in what it concealed, but in what it revealed. It arrived without intention, passed through without disruption, and departed without message. And yet through its presence it contributed to the growing mosaic of knowledge that connects us to the larger galactic story, a story written not in words but in orbits, molecules and light. Its silence was not emptiness, it was context. It was the quiet reminder that in a universe governed by laws we can decipher mystery and understanding coexist. As 3I Atlas receded from the Sun's immediate influence, its coma began a slow contraction, shedding fewer particles as solar radiation weakened. This gradual dimming marked the end of its most active phase, returning the object to a quieter state, more reflective of its long interstellar journey. Yet even as its visible features faded, the intellectual shockwaves of its visit continued to expand through scientific discourse. The object now functioned less as an active subject of observation, and more as a reference point and anchor for ongoing debates about planetary system evolution, volatile retention, and the broader architecture of galactic debris. The sheer antiquity of 3I Atlas remained one of its most striking attributes. If its origin within the thick galactic disk is correct, then its story begins at a time when the Milky Way itself was still settling into its current structure. The chemical environment of that early era, dominated by lower metallicity stars, more frequent supernova events and turbulent gravitational interactions, would have shaped any forming planetesimals very differently from the ones in our solar system. Thus, by measuring 3I Atlas's chemistry, scientists gained a glimpse into astrophysical conditions that no telescope, no spacecraft, and no simulation can fully reconstruct. The comet is not merely foreign, it is ancient in a way that stretches beyond human conceptual frameworks. It reflects a chapter of galactic history that predates not just Earth, but the very molecular cloud from which the Sun emerged. This realization invites a broader contemplation of time that contrasts sharply with human experience. Civilizations rise and fall on the scale of centuries. Biological evolution unfolds over millions of years, but interstellar objects like this one carry memories that span billions. Each volatile trapped in its structure, each molecular signature etched by radiation, represents a fragment of a timeline so vast that human history shrinks to a barely perceptible flicker. And yet, through spectroscopy and orbital modelling, human observers can decode portions of that immense timeline. The contrast between the brevity of human existence and the depth of cosmic history does not diminish us. Instead, it reveals the astonishing reach of our curiosity, our ability to interpret phenomena that exceed our lifespan by orders of magnitude. The interplay between scientific precision and philosophical reflection also became apparent as researchers analysed the implications of detecting multiple interstellar objects within a single human generation. Until 2017, none were known. Now it appears increasingly likely that such visitors are common and have always passed through our solar system not unnoticed, but unobservable with earlier technologies. This shift mirrors the transformation that occurred when the first exoplanets were discovered. For centuries, their existence was assumed but unverifiable. Then technology advanced, and within a few decades, thousands were detected. A similar transition is happening now with interstellar debris. The cosmos has not changed, our tools have. With future observatories, particularly the Rubin Observatory's legacy survey of space and time, scientists anticipate discovering dozens of interstellar objects each year. If this prediction holds, the 3 known objects so far will appear less like outliers and more like the first entries in a vast catalogue. Statistical patterns will emerge, typical compositions, velocity distributions, structural variations, and perhaps rare but significant anomalies. The presence of just a few outliers among thousands of natural interstellar comets could reveal formation environments or astrophysical processes never before identified. In this context, 3 Atlas serves as an early data point in an emerging discipline, a precursor to a future in which interstellar materials become a routine area of study rather than an anomaly-inspiring speculation. Even so, the public fascination with extraordinary explanations persists. Some interpret the increasing number of interstellar detections as evidence of artificial origin or deliberate timing. In scientific terms, the explanation is simpler detection capability increases, so discovery frequency increases. But in psychological terms, the timing matters because it coincides with a period of rapid technological acceleration on Earth. Humanity's ability to monitor the sky has never been greater. The alignment of technology and discovery creates an illusion of external intent where none exists. This is not a failure of logic. It is natural human tendency to interpret coincidence as pattern. Scientists, however, remain cautious in denying the possibility of technological artifacts outright, not because they find such scenarios likely, but because scientific integrity requires openness to all hypotheses until evidence excludes them. Yet the burden of proof for artificial origin is immense. It requires not just unexplained anomalies, but positive evidence of intent signals, structured design, propulsion signatures, or behaviours incompatible with natural physics. 3I Atlas produced none of these. It behaved as a natural comet should, passive, predictable, indifferent to its observers. Nonetheless, by confronting these speculative interpretations, researchers refined their understanding of what would constitute evidence of artificiality, and in doing so sharpened observational methods that may prove important in the future. Interstellar objects provide a practical testing ground for distinguishing between natural and artificial signatures. The discipline of astrobiology, long constrained by the absence of tangible samples from beyond the solar system, benefits from these visitors by examining compositions that reflect alien planetary environments. The boundaries between planetary science, cosmochemistry, and SETI become more permeable as each field contributes specific methodologies to interpret the same object. This interdisciplinary convergence becomes especially important when considering the chemical anomalies detected in objects like 3I Atlas. While fully explainable through natural processes, they raise the question of how chemically diverse interstellar planetesimals might be. If certain stellar environments routinely produce CO2-dominant comets, others may generate bodies with unusual carbon chains, nitrogen-bearing ices, or complex organic molecules yet to be detected. The more interstellar objects discovered, the more likely it becomes that some will display signatures that challenge existing classifications. Such findings would not imply artificiality, but they would prompt revisions of chemical models requiring scientists to expand their understanding of planetary formation under diverse galactic conditions. The prospect of capturing or sampling an interstellar object remains far beyond current technological capability, yet the theoretical frameworks are already being developed. Concepts like gravitational focusing high-speed intercept trajectories and cryogenic sample return protocols are discussed not because missions are imminent, but because the scientific value of such a sample would be unprecedented. A physical fragment from another star system unaltered by Earth's environment, preserved in interstellar cold, would offer a direct window into alien planetary chemistry. Even a milligram of such material would constitute a revolution in cosmochemistry. 3I Atlas will not be captured, but future visitors with slower velocities or favourable approach angles might one day make such a mission feasible. As 3I Atlas's brightness faded and its coma dispersed into the vacuum, the object's scientific narrative entered its final stage. The comet would soon transition from an observed phenomenon to a modelled one. Equations would replace images, orbital predictions would substitute for direct measurement, chemical ratios would persist only in published spectra and archival databases. Its influence would shift from active observation to long-term implications. Yet even in its fading, the object continued to embody the extraordinary intersection of time distance and physics that defines interstellar phenomena. It reminded humanity that the boundaries between star systems, though vast, are not impermeable. Material weaves through the galaxy, crossing light years as effortlessly as dust floating in a sunbeam. And with this reminder came an implicit message that needed no author. The universe is fundamentally connected. Processes occurring around distant suns can shape objects that eventually arrive at our doorstep. The chemical fingerprints of stars born billions of years ago survive in fragile ices that pass before our instruments, and even objects shaped by environments unimaginably remote obey the same physical laws that govern familiar comets orbiting our sun. The fading glow of 3I Atlas did not signify the end of its significance. Instead, its departure underscored the continuity of exploration. The comet becomes part of a tapestry, one thread among many woven through the collective effort of thousands of researchers, instruments, and observations. Its legacy is not spectacle, but understanding. Not disruption, but context. As 3I Atlas receded even further into the outer solar system, its trajectory gradually regained the quiet anonymity it had known for most of its existence. The powerful telescopes that once captured its detailed spectra now registered it only as a diminishing point of light slipping back toward the vast reservoir of interstellar darkness. This slow fading, though inevitable, marked a subtle shift in how scientists and observers perceived the object. While its physical presence diminished, its conceptual influence continued to expand, occupying a growing place in discussions about interstellar dynamics, cosmic chemistry, and the evolving capabilities of astronomical observation. In many ways, the most meaningful legacy of 3 Atlas lay in the methodology it forced the scientific community to refine. Each interstellar visitor challenges researchers to adapt techniques traditionally tailored for solar system bodies. Standard comet models must be expanded to account for unknown formation environments. Spectral libraries must include compositions that may not exist naturally in our own system. Orbital determination procedures must consider trajectories shaped by gravitational events too distant to reconstruct. Every adjustment made for 3I Atlas contributes to a more flexible framework for future discoveries. With each interstellar object studied, the tools of planetary science become more robust, more adaptable, and more capable of interpreting the diversity of the galaxy. The assurance with which the scientific community managed the speculative narrative surrounding 3 Atlas also revealed something important about the state of modern science communication. In earlier eras, the unusual characteristics of such an object might have sparked widespread fear or fantastical interpretations rooted in superstition. But in this era, researchers answered speculation not with condescension, but with clarity, explaining, contextualizing, and distinguishing between phenomena that appear extraordinary and those that truly demand reconsideration of physical laws. The effort required patience, but it demonstrated that transparency and calm explanation can coexist with public fascination. The object thus served as a test case for navigating the boundary between scientific rigour and collective curiosity. As the comet's visibility declined, the focus of researchers shifted toward constructing theoretical simulations that could explain its measured properties in the context of galactic evolution. By inputting its velocity, orbital inclination, chemical signatures, and estimated size into computational models, scientists attempted to backtrack its path, not in the literal sense of reconstructing its exact origin, but in the probabilistic sense of identifying the kinds of stellar environments that produce objects with comparable characteristics. The thick disk scenario remained the prevailing interpretation, but simulations also explored alternate possibilities: formation near intermediate mass stars with unique volatile gradients, early ejection during planet migration events, or reshaping through repeated exposure to cosmic rays during prolonged residence in the galactic halo. The modelling also highlighted how gravitational interactions over billions of years can accumulate into the high speeds observed in some interstellar bodies. Simulations revealed plausible sequences of close stellar flybys, each exchanging small increments of momentum that could gradually elevate an object's velocity to the level measured for 3I Atlas. These flybys scattered across millions of years do not require improbable alignments or exotic events. They represent the natural dynamical churning of the galaxy, where stars pass one another at varying distances, and their gravitational fields subtly alter the trajectories of any objects drifting nearby. This cumulative influence explains not only the comet's velocity, but also its unusual approach vector relative to the galactic plane. The more researchers reconstructed, the clearer it became that 3 Atlas was not simply a representative of its origin system, but a witness to epochs of galactic evolution. It traversed regions where stars were more densely packed environments, where supernova explosions reshaped surrounding molecular clouds, and gravitational corridors, where the Milky Way's spiral arms influenced stellar motion. It has passed through ionized regions, dense molecular filaments, and open interstellar voids. Each environment contributed to radiation processing, surface erosion, and chemical alteration. These processes, spread across vast timescales, collectively shaped the object that appeared in our sky. Thus, studying the comet's present state reveals a kind of accumulated biography, a record of environments it experienced during its migration through the galaxy. At the same time, the lack of alarming anomalies reaffirmed a reassuring truth: extraordinary cosmic phenomena can be remarkable without being threatening. The absence of artificial signals, controlled maneuvers, or engineered patterns does not lessen the object's significance. Rather, its entirely natural origin underscores the richness of the universe's processes. The galaxy does not need intention to produce objects of profound scientific value. Randomness shaped by physics yields outcomes that provoke wonder without requiring anything beyond natural laws. This recognition also influenced discussions in fields beyond astronomy. Philosophers of science noted how interstellar visitors challenge assumptions about typicality, what counts as normal in a universe as diverse as ours. When the first interstellar objects were discovered, they seemed extraordinary because they defied expectations built on solar system examples. But as more are detected, researchers increasingly suspect that the apparent regularity of solar system comets may itself be an anomaly. The galaxy may host far more chemical and structural diversity than the solar system alone reveals. This shift reframes how scientists interpret not only comets, but the conditions under which planetary systems form and evolve. Sociologists and anthropologists also found interest in how humans responded to the object. The blend of fascination, anxiety, and curiosity revealed deep patterns in how humanity processes ambiguity. Even when data consistently supported a natural explanation, the impulse to imagine agency remained strong. This impulse is not necessarily irrational. It reflects the human tendency to treat the unfamiliar as meaningful, even when meaning is supplied by interpretation rather than observation. Three-Eye Atlas thus becomes a case study in how scientific discovery interacts with cultural psychology, illustrating how knowledge and imagination influence one another. Meanwhile, the technical challenges of observing such a fast-moving faint object prompted improvements in detection algorithms and data processing pipelines. Machine learning tools designed to identify interstellar trajectories became more sophisticated as they incorporated Three-Eye Atlas's motion characteristics into training sets. These tools will enable shorter detection to confirmation times for future interstellar objects. The faster humanity detects such visitors, the more effectively observational resources can be allocated to study them before they fade. In this way, each interstellar object improves the scientific infrastructure needed to study the next one. Even the questions the comet did not answer proved valuable. Many uncertainties remain unresolved: the precise thickness of its volatile layers, the detailed structure of its nucleus, the exact ratios of isotopes that might reveal more about its formation environment. These unanswered questions are not failures, but opportunities, markers of where future instruments must improve. As astronomers look ahead to next-generation observatories, the limitations encountered with Three-Eye Atlas help define what capabilities will be most important: higher spectral resolution, longer infrared baselines, faster response times, and telescopes capable of imaging faint objects in close solar proximity. In the background of these scientific advancements, the public continued to follow updates about the object with a mixture of awe and contemplation. While the speculative narratives that accompanied its arrival gradually faded, what remained was a quieter, more grounded form of wonder, the recognition that humanity had witnessed something ancient, remote, and impartial. The comet's presence did not signify message or intention, it signified scale. It reminded observers that the galaxy operates on timelines and distances that dwarf human concerns, yet remains intelligible through persistent study. As the object finally crossed beyond the reach of most telescopes, it transitioned into the realm of prediction and memory. Its path through the solar system is now a completed chapter in its long journey. Scientists can project its course into the future with confidence it will drift outward, accelerate slightly as it escapes the sun's weakening pull, and resume its silent passage through the galactic medium. In a few thousand years, it will be indistinguishable from the uncountable other fragments of ancient worlds scattered throughout the Milky Way. Yet for humanity, its brief visibility will persist indefinitely in the form of archived spectra, refined models, and published papers. Every future researcher who studies interstellar chemistry will encounter the data from Three-Eye Atlas, just as they study the data from Borisov and Oumuamua. Each object contributes a piece to the emerging mosaic of galactic diversity, and each one, by merely existing, expands the horizon of what is scientifically imaginable. As the trajectory of Three-Eye Atlas carried it deeper into the outer solar system, its observational certainty gradually surrendered to statistical projection. The comet's brightness dropped below the threshold for routine monitoring, leaving astronomers with only intermittent glimpses through long exposures or archival analysis. Yet its scientific relevance did not diminish. Instead, its departure marked the shift from real-time observation to long-term interpretation, an intellectual phase in which conclusions are distilled, models are refined, and the object becomes part of a larger conceptual framework rather than an isolated event. This transition mirrors the natural progression of scientific inquiry. When a phenomenon is newly discovered, attention focuses on immediate data, position, brightness, spectral features, dynamical behavior. As the dataset grows, questions evolve from what is it doing now to what does it represent, and eventually to what does it teach us about the universe. In the case of Three-Eye Atlas, the answers to these later questions proved more profound than any initial anomaly might have suggested. The object's significance rests not in its rarity, but in how effectively it illuminated the processes and conditions that shape interstellar debris. Researchers began integrating the comet's characteristics into broader models of galactic material exchange. These models simulate how stellar systems interact through gravitational slingshots, molecular cloud, drift shock waves from supernova explosions and tidal forces exerted by the Milky Way's spiral arms. In such a dynamic environment, comets and planetesimals are constantly being displaced, scattered, and sometimes ejected entirely. The objects that eventually reach regions like the solar system do not represent the average outcome. They represent the survivors of violent, prolonged and selective processes that filter out fragile or unstable structures. 3 Atlas, therefore, is not simply an example of interstellar debris. It is evidence of resilience on astronomical timescales. For billions of years, it endured radiation fields strong enough to erode molecular bonds, navigated regions of space dense enough to fracture weaker objects, and survived close encounters with stars capable of completely altering its path. Every volatile trapped beneath its surface implies protection against cosmic forces that would have destroyed a less robust nucleus. Even its unusual carbon dioxide dominance may be a consequence of selective survival. Perhaps only objects with significant CO2 reservoirs endure the thermal stresses of repeated stellar encounters. In this sense, chemical anomalies become signatures of endurance rather than clues of intention. The implications of this dual history extend beyond planetary science. They shape how researchers think about the distribution of organic molecules, water ice and carbon-based compounds across the galaxy. If objects like 3I Atlas routinely carry volatiles formed around distant stars, then the raw ingredients for prebiotic chemistry may be distributed far more widely than previously assumed. In this interpretation, the galaxy functions as both a mixing chamber and a delivery network, exchanging materials between stellar neighbourhoods over billion-year timescales. Even without invoking panspermia, the exchange of chemical precursors becomes a natural consequence of cosmic dynamics. The presence of interstellar comets in the solar system thus becomes a tangible link in the chain of material continuity that connects different regions of the Milky Way. Meanwhile, engineers and mission planners began considering the technological implications of interstellar objects. Although it remains impossible to intercept a fast-moving object like 3I Atlas with current propulsion systems, the idea of intercepting future slower interstellar visitors is no longer confined to speculation. Concepts for rapid response probes, high-thrust propulsion systems, and autonomous intercept trajectories are being explored in preliminary form. The lessons learned from the limitations of observing 3 Atlas drive these designs: the need for rapid launch capability, wide field, early detection, and instruments optimized for studying volatiles at high relative velocity. In the long term, such missions would enable humanity to sample matter from beyond the solar system, directly, a capability that would transform cosmochemistry and astrobiology. Yet even as discussion shifted toward future opportunities, there remained an undeniable philosophical dimension to the comet's departure. Observational astronomy is inherently transient. Comets flare brightly for a moment, then fade into darkness. Supernovae blaze for months, then collapse into silence. Interstellar objects visit briefly, then vanish into the void. The impermanence of these phenomena mirrors the impermanence of human perception. By the time another object comparable to 3I Atlas passes through the solar system, the individuals who observe this one may no longer be alive. Astronomy is therefore a discipline built not only on measurement but on generational continuity. Each discovery becomes a gift to future researchers who will inherit the models, datasets, and hypotheses left behind. The comet's receding trajectory prompts a final recognition. Even after its light disappears, it leaves behind a shape in human understanding, a contour in the intellectual landscape that did not exist before. It reminds us that cosmic history is not written only in stars and galaxies, but also in fragments of ice and rock that wander across the galaxy, carrying chemical memories of suns long extinguished. To witness such an object even briefly is to glimpse the continuity of cosmic evolution. In the end, 3I Atlas taught us exactly what it was meant to teach: that the galaxy is richer than our assumptions, that natural processes can produce wonders beyond expectation, and that the pursuit of understanding is itself a form of cosmic participation. It reminded us that we are observers in a universe that does not explain itself willingly, but reveals its truths to those who look carefully, patiently, and without fear. And so the final chapter closes not with revelation, but with recognition that this brief encounter, this passing traveller, was simply one thread in a universe woven from billions of such threads, silent, ancient, and endlessly instructive. Its journey continues unchanged by our observations, indifferent to our interpretations, yet immeasurably valuable for the clarity it leaves behind. Traveller, as Atlas, dissolves into the outer dark, leaving nothing behind but a faint trail of memory across our instruments and our thoughts. We find ourselves standing at the quiet edge of its story and yours. For hours we have followed it together, drifting through distances so vast they cannot be spoken, through questions that stretch beyond certainty, through the soft places where science meets wonder. Now, as this ancient visitor retreats into the silence that shaped it, we realise something subtle. The journey was never only about the object. It was about the act of observing, the act of listening, the act of allowing the cosmos to move through us as gently as it moves through space. 3 Atlas asked nothing from humanity. It did not threaten, did not signal, did not alter its path for our sake. It simply brushed past our sun, the way dust brushes past a candle flame, quietly, obediently, beautifully guided only by forces older than any language we know. And in that quiet obedience lies a kind of wisdom, a reminder that even the most extraordinary things in the universe move with patience, not urgency. That age does not hurry. That distance does not shout. That meaning does not require intention. As it fades, observer, it leaves us with the soft truth that the cosmos is still unfolding, still breathing, still writing itself in particles of ice, in invisible radiation, in the long gravitational arcs that carry wanderers from one side of the galaxy to the other. We are small beside these motions, yes, but not insignificant. For we are the ones who watch. We are the ones who wonder. We are the ones who turn cold data into understanding and understanding into meaning. Even in our fragility, we remain the only creatures we know who lift their eyes toward the dark and ask gently, "What is out there?" So rest now, listener. Let the last traces of this ancient traveller settle into the back of your mind like dim starlight. Let the vastness soothe you rather than overwhelm you. Let the unanswered questions keep you company instead of keeping you awake. The night is long, the sky is calm, and the universe in all its silence, all its distance, all its mystery will keep watch while you sleep. Stay curious. Rest well, traveller. If this story found you tonight, you may stay for the next.